All right, so today we will be talking about data augmentation. So as you are already starting to become aware of, the data is the most important thing in these machine learning algorithms. I mean, yeah, it is important us as designers making choices and choosing the right parameters, hidden nodes, and implementing things well. But really, you know, garbage in, garbage out. So you have to have good and lots of data. Okay, so like I've said before, one of the reasons deep learning and there's a resurgence of machine learning and all that is because of the internet making more and more data available, making large data sets available to everyone to benchmark against. That's, you know, one of the big things. But there are plenty of times when even the amount of data that you can get, you know, still isn't enough, or it's hard to get the data, or you can't get the data. And there's things you can do to try and make your algorithms more robust and to be able to be more generalizable. Because, you know, we talked about this probably the very first day, where you make your machine learning algorithm, you have a certain amount of training data, and you use that training data to set all the parameters in your machine learning algorithm, and then you use that on new data. And hopefully you are able to, your algorithm is able to generalize well, that the training data gives all of the possible combinations and situations that you could have. Okay? Of course, that may or may not be true, whether that's going to happen. Oh boy, I don't dare touch that little thing there. How do we make that go away?
Like on the PowerPoint?
Yeah, let's try that. No. What does that do? Minimize. That shouldn't pause, right?
Shouldn't.
All right, we'll take our chances. All right. So here's a situation where we got, I don't know, what is that thing? A quokka?
Yep.
Okay, well, thank you.
I've seen this picture on the internet a lot.
Is it from Australia or something?
I think so.
All right, well, I wouldn't have known. I know a lot about animals, I used like to think, but I didn't know it's a quokka. So here's this quokka, and if we're trying to you know, classify whether we have an image that is a quokka or is not a quokka, you know, I don't know, maybe, I'm not sure what is the actual original image. Maybe this is the original image. But it's pretty obvious to the human. You look at all of these, maybe that one's kind of dark, it's kind of hard to see, but all of those things are quokkas. Okay, and with this one image, it would be nice if we could do all sorts of distortions and changing this around and add more data to the training data, so that it'll be able to recognize a quokka not just standing straight up and everything pretty, you know, but in all sorts of different situations. And so you know, this is all artificially created data. You know, we call that data augmentation, where we might zoom in or zoom out or shift or flip or rotate or shear. That turns rectangles into parallelograms. You know, if we smooth it out or sharpen it, do different things. Now, all these images are still these quokkas, and it would be nice if we could make our algorithm be able to detect all of these. And so that's one of the things that's come about in recent years is this idea of data augmentation, that you only have a finite amount of training data, and you can go ahead and change it and manipulate it in all these different ways, and that will make your algorithm, your machine learning algorithm, more generalizable, that it can detect more quokkas than it could before. Okay? Now, for classification, this works really nicely because, you know, the labels for all of these are still, yes, it's a quokka. Okay? But if we have regression, that gets a little trickier because, you know, if I'm going to change something, I need to know what the label is going to be for that continuously changing variable that's supposed to be the output. In our case, it's not so difficult. You know, we have that Roomba in one particular position, and if we rotate it, because that's how we're going to create our artificial data in this problem, is by rotating it. And if we rotate it, we know the angle that we rotated it at, and the angle of rotation is what we're trying to have as our label. So that's not a big deal. But it might change, you know, it might depend. Other problems might have other things that are important, okay, to get those labels. Now, this is pretty much, you know, for this problem, we're just going to do some rotations, and that's pretty straightforward. In the end of this lecture, I'm going to show how we do image rotations pretty easily in OpenCV. But I want to go ahead and give you another example of the power of how you can add augmented data to solve some pretty interesting problems. Now, I work in self-driving vehicles, and one of the things you might like to train a neural network is to do an end-to-end algorithm for how to determine what the steering command should be. Okay? And when they say end-to-end, basically what they want to do is they want to put an input image as the inputs, and all the pixel values in that image are the inputs to your machine learning. And then your output is going to be a regression task for how much should the steering wheel be turned. And so that's end-to-end in the sense you don't do anything else. You just put in the image and you get out the steering command. And so one of the ways that they go about this is they'll get a human in the car, and they'll have a human driving, and they'll just record what is the image out the front of the car and what is the steering command that the human is doing. Okay, and that's great, and then we can just drive and get tons and tons of data however long we want to drive and log this information for. And that's great, but what happens is that if the car gets in a situation that the human has not driven in, then the algorithm doesn't know what to do. So if, for example, you drift, you know, the human, you know, if you just drift off to the side, your image is going to be different than what it's been, what it's trained on, and it won't necessarily know the right command to do. Now, obviously, you don't want the human to just go around and drive back and forth, because then it'll learn to swerve all over the road. Okay, so so that's a tricky problem. And one of the ways that they solve that is they'll mount three cameras, one in the middle that's actually what's being used, and then they'll mount some on the sides that get a little different perspective that make it appear as if the car is not in the middle of the road anymore. Okay? Now, we still have to decide, well, what should the steering commands be for them? And you can do some things with the vehicle dynamics and say, okay, well, if I'm here in this position, I want to put in a steering command that gets me back to the middle of the road in half a second or something like that. But we have to come up with some way of deciding, what should those values be. Okay? Now, that's sort of half artificial data. I mean, it's artificial in the sense that it's not what's coming out of the middle of the camera, but it's actually being measured, but we're giving it artificial labels. Another thing we could do is, instead of having those extra cameras out there, we could, knowing the perspective transform of the way the image is formed, we could literally create artificial data for what the image would look like if I'm, for example, if I move the camera, if I move the car 5 feet to the left, or move the car 5 feet to the right, or even rotate the car a certain angle, and we can, through the image processing, be able to determine what the new image would look like. So that is pretty cool. So if we go back to this idea of the image, the perspective transform of going from my real point, big X, big Y, big Z, to my image point, little x, little y, we have these relationships for how to go from the big values to the little values. Okay? And so we want to ask the question, so given a pixel in the image, little x, little y, and it has a particular real position, big X, big Y, big Z, and what would the position in the image be if its real position moved by d amount in the x direction? That's laterally. Okay, so it stayed in the same height above the ground, and it stayed the same distance away, but we shift it laterally by some amount d. All right, so where in the image would that point appear if it got shifted by this amount d? And that's the question we're trying to answer. Okay? So at least for the y is not going to change because y and z, we're assuming the y and the z position, the real space, don't change. And the little y position only depends on those. So the new y position, y prime, will be the same as the old y position. So that's nice and easy. Then for the x, okay, the new x position, that's going, in the image, the x prime in the image is going to be the old real x position plus however much I want to shift it in the real world. Now, we can go ahead and replace the old x position knowing the old pixel position, little x. So we know little x and little y, that's where the point originally is, and we're trying to find x prime, y prime, where it would be if I shifted d in the real world. So we go ahead and replace in the big X, which is where it was before, okay? And then you can see we can bring the F into the numerator. It cancels that one, but then is multiplied by the D. Okay, so there's my X prime. So basically, I need to know where was it, what was its distance before from the camera in terms of Z, and where was it in the image before. Okay, now let's say I don't know how far from the camera it was. Okay, I can replace f over z. I can rearrange this equation here to get f over z being little y over big Y. Okay, because little y I know where it was originally in the image, and big Y, as we'll find out, basically I know that it's that point. If that point is on the ground, it's some distance. It's the distance the camera is above the ground. So in the end, we're going to know what big Y is, and that equation is going to be more useful for us. Okay? Now, we need to be able to deal with all points, and we're going to do two things. Make two assumptions, and these are assumptions. You're going to see it's going to warp the image that we get in the end, but we'll assume that everything that is above the horizon, and I'm going to define that as the middle of the image, the middle of the image, because if I'm parallel to the ground pointing straight ahead and I'm on flat ground, then everything above halfway in the image is going to be above the horizon. Everything below is going to be obviously below the horizon. So we're going to assume everything above the horizon is infinitely far away, that it has a big Z equals 0. And so I can take this equation here and I can plug big Z into there. And if I do that, what I end up with is that the x position in the new thing is the same as the x position in the old thing. Now, this is interesting. This is brings me back to one of the big things I always thought about when I was a kid. I don't know if you guys thought about this stuff, but I'm driving in the car with my parents, and like all the trees are like zooming past me, and the sun doesn't move. Right? Everybody wonder about it? Is this thing parallax? Is this geometrical thing called parallax? And basically, if the sun were to move 5 feet from its current position, it wouldn't move in my image. Okay? And so that's sort of what's going on here. So if something's infinitely far away and it moves, it's not going to move relative to what we're seeing. Okay? So that's great. Anything above the top half of the image stays the same because the big X, X prime and Y prime stay the same. Now, anything below the horizon we will assume is on the ground. Now that's not true because there's going to be road signs and cars and some things, but we're going to make this assumption that everything below the ground, that its Y position is at the height of the camera above the ground. So that gives us this expression here, where D is the amount I'm trying to move the car or camera, H is how high the camera is above the ground, little x and little y were the original positions of the pixels. So now, I can take every pixel in my image, in its little x, little y, and I can say if I move the camera d feet in one direction, where in the new image would that be? X prime, y prime. So I can take that pixel, and whatever that pixel's value is, I can move it to this new place in the new image. Okay? Now, we're going to end up with some issues where it's going to move to a fraction of a pixel position. We'll have to split up, put some of it in the other, and you can look at the code. I did the code for this, and you can look at it on how I did that. But at least in the concept now, it's not hard. Every pixel, I find its x and y position, I map it to a next x prime, y prime, and I create a new image with that pixel value in the new place. Okay? Then, what if we rotated? So we've got our car driving out there, and what if we rotated it, and that's in the big X, big Z plane. So what if we rotated it in the big X, big Z plane, keeping its Y position the same? Okay, its big Y position the same. So where would X prime, Y prime be if we had a rotation of some theta in the XZ plane? So we need to know, what is this new position, X prime, Z prime, where the Y stayed the same, because we're not rotating in that Y direction. So here is the rotation matrix. You recognize this from 3710, or I introduced it a little earlier. I think this one might be rotating in the opposite direction. If you go back to the other slides, I think there's signs and minus signs that are switched around, and that's just changing the direction that the rotation happens. Okay? So I have my original space in the real world, my final space in the real world after the rotation. So I can break this matrix into two equations for the new X prime and the new Z prime, okay? And then I can go and say, okay, well, my new position in the image is going to be dependent on the new real position in the X and the Z places. And I have now expressions for what those X primes and Z primes are. I plug them in. Okay, then I take my X just like I did before, and I replace that with the original, that's the original position in pixels in the image. And then I can bring the F through. The F can multiply in there, cancel that, the F ends up here. You'll notice this is really convenient that the Z divides out on the top and the bottom, because in general we don't know where that point is in the real world in distance from the car, but it's nice that that goes ahead and cancels out. So the new position for X is the old position of X and the focal length, which we talked about how we can get with the degrees, angles of view, and that sort of thing. And of course, however much theta is supposed to rotate. And we can do a similar thing for the Y position. Okay? And it's new Y prime, it's new Z prime. I go ahead and replace the Y. That one's easy because the new Y prime is the same as the old Y. So I can go ahead and put in the old Y information, and then I can go ahead and replace the X in there as well, and then the Z's again cancel out. We move around where the F's are, and there's our final result. So now I know where my new X and Y positions are given my original ones and how much I want to rotate and the focal length. So here's the results, and it's quite amazing. I was really amazed when I worked this out and I actually got it to happen. It's really cool. So here's the original image, okay? And I'm going to shift the camera to the left. So the lane width is usually about 12 feet. And if I'm driving down the middle of the lane and I shift 5 feet to the left, I should be basically driving down the center line, okay? And the magenta box here is the original position. Okay? And so you can see here, I'm basically driving down the middle of the lane. Okay? Now, what has happened? First of all, you can see anything above, the top half hasn't changed. So the top half of the image hasn't changed. Okay? Things that are not on the ground that are in the bottom half are distorted. So you look at the car, where the car is below the horizon, it's gotten distorted. It looks like a parallelogram. It's gotten sheared here. Okay? And then we have this black piece here. And that's the fact that if I shift to the left, there's going to be parts that I can see shifting to the left that I can't see right now in the original image. So there's no way for me to know what this stuff looks like because that's not in the original image. Interesting. Okay? In the same way that when I shift to the right, things that were, this stuff here that was in the original image, I can't see that anymore, so it's outside the image. Okay? So when I shift over, some of the stuff I could see, I can no longer see, and some of the stuff I would like to see, I didn't see before, so there's that black stuff in there. Okay? But it's really quite amazing. I mean, that looks, I mean, if you ignore the car being sort of distorted, it looks pretty darn good, doesn't it? It's really interesting how it works out nicely that way. Okay? So then let's take this image here, and let's rotate it back to rotate to point 20 degrees back towards where I came from. So I'm still actually driving, I'm still located at the center of the lane, but I'm turning away to look back where I came from. Okay? And so this here is now what I can see when I turn back. So I'm still headed straight down the middle of the lane, but I've turned to look 20 degrees the other way. Okay? And what's interesting, and you'll notice that when I did the first translation, I kept this part of the image, because when I rotate back, I'm going to see some of that again. So I kept, before I did my second operation, I kept this whole big thing, even though what I can really only see at any point in time is what's in the magenta box. And so this stuff comes back into view, okay? And the stuff that I couldn't see anymore goes back out of view. So this right here is this image shifted to the left and angled 20 degrees, and that's what the image would look like. And of course, some of the stuff I won't be able to see, because if I rotate that 20 degrees, there's stuff that wasn't in the original image. So this is still pretty neat that I can start off with the original image, know stuff about the perspective transform, and show what the image would look like if I moved around, which is really pretty amazing. So there's lots of cool stuff. We're proposing a master's program that who knows when it might start, but maybe within a year or two. And one of the courses that I would be responsible for is a machine vision course, and so we do some stuff like this in that course. Would be pretty neat. Okay, so it's quite amazing all the different things that you can do, and it's pretty cool. So that's sort of an aside. It's interesting, and might get you motivated to do some more stuff. But at least for the task at hand, what we're interested is doing a rotation. Take this Zumba and rotate it. Now, this is the equation that we used before when we were doing an image rotation and then a translation after the rotation. You'll remember we sort of went through the process of where this thing comes from, and we got this matrix, this rotation matrix, etc. And so in OpenCV, they do all sorts of transforms with matrices. And there's all sorts of different transforms, and it will give you the matrix. And if you don't ever pay attention to the details, you might not even care. You might not even notice what the size of the matrices that they return are. In this case, to do this rotation and then translation, it's a 3x3 matrix. Okay? Now, what we're interested in doing is taking one of these images. This is Roomba 2. It's one of the 2 images I've given you to get training images from. And what I'm going to do is I'm going to have this thing rotate about this point right here. That's the point 5100 in the original image. And if I want to get this image to rotate about that point, I'm going to use this CV2 get rotation matrix. And I need to tell it what point I want to rotate about. I need to tell it what angle I want to rotate it, and I want to tell it how much I want to scale it. So not only could I do a rotation, but then I could shrink it or make it bigger. And in this case, we want to keep the same scale, so we just have a scale of 1. Okay? Now, I went ahead and displayed the image here, first of all, in Figure 1, and that's what you're seeing here. Then I print on the screen what the rotation matrix M looks like. And then I do an affine warp. And an affine transformation, basically it's a linear transformation, a linear matrix transformation, where it has a slope and an intercept essentially, but then it scales into this matrix space. But essentially the way you do this, you say, well, what image do you want to apply this matrix to? In our case, it's a rotation matrix. That's how we got the matrix. But there's lots of other types of M's that you can use with warp affine. So I say I want to take my original image, I want to use this matrix, and then you say the shape of the output image that you want. And I just said I'm going to use the same shape as the original. Okay? Now, in PowerPoint, I took this image and I rotated negative 30 degrees about that point. So in PowerPoint, I went ahead and took that image and I rotated it, keeping, this is the original shape where the magenta was. Then, after I took this rot image, after I've warped it, and that's what I'm now going to display for you. So now you can see that's what gets displayed when I rotate 30 degrees. Okay, so some of the stuff from the original image is gone because I've said what the shape is. I've given the shape to be just the original size, so things that rotated out of the image are gone. And there's more black space that comes in, that was originally not in the image at all. Okay, so that's pretty straightforward. We just say where the point is about which I want to rotate, and I say how many degrees I want it to rotate. In your situation, you're going to rotate about the center of the image. I've gone ahead and put the image in the middle of there, and so you're going to want to rotate it about the center, and you're going to rotate it 1 degree, 2 degree, 3 degree, 4 degree, 5 degrees, and save each one of those images so you have an image for each one of those rotations. If you care to know, okay, which in this case you could remain blissfully unaware, okay, because you're just going to use get the matrix transfer, get the rotation matrix, and then do the warp affine. But as it turns out, this is a 2x3 matrix. I'm still multiplying by the x, y, and the 1. Okay, that's why there's 3 columns. But there's actually only 2 rows, and in the end, I get just x prime and y prime. There's no extra row in there. For whatever reason, that's the way the rotation matrix works. And really what's happening here is that you take the image and you're going to translate it back so that this magenta point is actually the origin. So if you translate it so that point's at the origin, then you can apply a standard rotation, and then you just need to shift it back to where it was. Presumably, I don't know for sure, but I'm pretty sure that the results of this matrix do those things of shifting it, rotating it, and then shifting it back. Okay? But like I said, it doesn't even really matter. But if you're curious, I was curious. I wanted to see what that rotation matrix looked like, and I was surprised that it wasn't 3x3. But OpenCV handles all that stuff internally. Okay? So that's what I wanted to show you today about the data augmentation. What we're doing is pretty simple, just rotating these things. We do have a little more time, so I want to talk about some things in this project. And one of them is in how we're going to represent the labels. Okay? So in the end, I don't know, that picture's probably too small. But in the end, you're going to have 360 values for, you have 2 images. You got Roomba 1 and you got Roomba 2. And you're going to be able to make 360 images out of each of those for angles of 0 to 359. Okay? And the label that we want is the angle. Okay? And you'll also notice I asked you to go ahead and when you save those images to save them with underscore and then the value for the degree. That way you can build the label matrix automatically from the file name. That's going to be easy for me because I'm going to have in the end to test it. I'm going to have these test images, and then it'll be test underscore and then the degree. And so you just load in each of those and you pull out the last piece on the end of the file name to get what the label is. Okay. Now, if we went ahead and trained our neural network on those labels, it would work pretty well, but there would be some problems around the 0 degree range, because you're going to have 0 degrees and you're going to have 1 degree, and then you're going to have 369 degrees, and all 3 of those images look pretty much the same, and they have pretty close to the same output, or they should. I mean, it's the same position. But one of them is 359, and the other 2 are 0 and 1, and there's a discontinuity involved there. And so what you would find is that you would get some really bad values at that around 0 and around 360. You get some bad predictions. So what I've suggested to do is to go ahead and instead of using that as the output, okay, to go ahead and think about having 2 outputs, okay, where we take advantage of the fact of using an inverse tangent, the 4 quadrant inverse tangent. So essentially, if we have the unit circle and you want to distinguish between 0 and 0 and 360, or say negative 1 degree and 1 degree, okay, they both have a positive, they both are positive for x, and their y's are about the same. Okay? And so what we can do is we can take the sine of the angle and the cosine of the angle. Because if I take sine of 1 degree and sine of negative 1 degree, I get basically the same result. Okay? It's close, because sine of x is equal to x. All right, so when it's around 0, sine of x is around 0. So if I take sine of x, it doesn't matter on which side of that thing I'm on. Okay, and if I use cosine of x as well, that will help me know vertically where I am. Okay, and so if I now have two outputs for my neural network, one where it's trying to be sine of x and another where it's trying to be cosine of x. So what the neural network is going to output is the sine of the angle and the cosine of the angle. Then what we can do to get the actual angle is we could take the inverse tangent of the sine over the cosine. Okay? And so the network's going to output these guys, which of course I know sine over cosine is tangent. Okay? So if I take the inverse tangent of that ratio, then I will get my theta. Now, there's a problem with that. And I don't know, are all of you familiar with the idea of a four-quadrant inverse tangent? Kind of, maybe, probably not. Okay? I had a lab, when I ran 4100, I had a lab where we went over that we could see that that's obviously a problem. But I'll show you a reason why the inverse tangent of the angle doesn't work out. I mean, first of all, the inverse tangent is only going to give you a value between negative 90 and positive 90. Okay? If you try every possible combination of y and x, your inverse tangent is only going to give you positive and negative 90. It's only going to be 180 sweep. Okay? And the reason for that is, here's an example. Let's say you've got sine is 1 and cosine is 1. So that's 45 degrees. Okay? And so that's in the first quadrant. Okay? Then if we look at sine of being negative 1 and cosine being negative 1, that's in the third quadrant. Okay? So 1, 1, that's when I'm, in my x and y. 1, 1 is when I go up here, positive 45 degrees. Okay? Then negative 1 is down here. Okay? So one is positive 45 degrees, the other is negative 45 degrees. And so the sine of, in the first quadrant, the sine is 1, cosine is 1. I divide the two, and then I'm asking for the inverse tangent of 1. Okay? In the third quadrant, I've got sine is negative 1, cosine is negative 1. I divide those two things. Negative 1 over negative 1 is 1. So then I ask for the inverse tangent of 1, which is going to give me 45 degrees. Now, it's the same line. It's on the same line, but it doesn't give me that third quadrant. Okay? Because the ones cancel. I don't know whether it's a positive 1 over a positive 1 or a negative 1 over a negative 1. Okay? So basically every device, whether it's your calculator or computer, has not only ATAN, or in NumPy's case, why do they have to write ArcTan? I don't know, NumPy has to have ArcTan instead of ATAN. I've never seen any other computer or calculator ever have it as ArcTan. But anyway, so there's ArcTan, where you pass to it y over x. Okay? Or you do ATAN or ArcTan2, ATAN2 or ArcTan2. And rather than dividing the two and passing that as a single argument, you pass the numerator and you pass the denominator. And it will go ahead and do the division, and it'll be able to check what the signs of them are and say, are they both negative? Oh, that's in the third quadrant. I need to make sure I return negative 45 instead of positive 45. Okay? So ATAN2 allows you to get 4 quadrants. You'll get not just negative 90 to 90, you'll get negative 180 to negative 180 for the full 360. Okay? Now, that is also a situation is that pretty much all the inverse tangents go from negative 180 to positive 180, and we're trying to do things 0 to 360. So essentially, anytime you get a negative value, just add 360 to it, and it'll bring you around. Okay? So basically, you do something like, where, do a logical indexing, where are all the values less than 0, and add 360 degrees to each of those positions. Pretty easy to handle. Okay? So we're then going to have the inverse tangent. Now, one of the other nice things about doing it this way is that if I instead was trying to do like sine and cosine, and then I tried to do like an inverse sine, because it's going to give me, the output is going to give me, the neural network is going to give me the sine of the angle and the cosine of the angle. And if I tried, instead of doing the inverse tangent, just do the inverse sine and the inverse cosine, that could tell me what the angle would be if I did each one of them individually. Okay? But the problem with that is that the neural network is going to be trained to give outputs between 0 and 1 for the sine of the angle. But because it's a regression task, it might actually have a value greater than 1. It might say 1.01 or 1.1 or something. And you can't take the inverse sine of 1.1. That will give you an error. But this is one of the really great things, is that if you take the ratio of the sine over the cosine, even if one of those two things are individually above 1, when you divide them out, the ratio is what we're interested in. And that ratio actually can be infinite. I can do the inverse tangent of infinity, and that gives me, what, 90 degrees, I guess, something like that. Okay? So by doing the inverse tangent, I avoid problems where the sines and cosines are outside the actual domain of what sine and cosine would be. Because you will have that for sure. And what's interesting, one of the things I did when I was first testing this out is I took each one of those sines and cosines and individually did the plotted the sines and the cosines, and you would expect them to be on a unit circle, but they weren't really on the unit circle. They were sort of all over, sort of around where the circle would be, because some of the ones were greater than 1, some was less than 1. They should all be, give me a radius of 1, but they weren't doing that because the neural network's not exact. Okay, but what I found is that if I just go ahead and take the inverse tangent, I get pretty reasonable values even if it wasn't on a unit circle. So it was kind of nice that the tangent sort of kills some of that stuff for you. All right, so this is going to be a multiple input problem. I'm suggesting just go ahead and use hog and color histogram features like we did last time, so you can just port that code back in, and just build your feature vector again from the hog and the color histogram. Okay, and so you've got all of your however many thousands of features you've got going into your neural network. Then we need to choose how many hidden nodes are we going to use, and then we have on the output, we're going to have 2 outputs. So one of the things to keep in mind here is that the actual error that the neural network is updating on is going to be how close is the sine and the cosine to what this neural network thinks the sine and the cosine are. So it's actually not, it's not driving the gradient for the error with how close is the angle correct. It's saying how close is the sine and the cosine to being correct. So if you looked, and I'm not sure, I haven't done that recently, but there's a way where you can get it to display what is the actual loss, what we call the loss, the error function. What is the error function's value? And that error function's value, you'll see, it gets smaller and it gets smaller and it gets smaller, but what does it mean? If I just look at the number, oh great, it's 0.01. So what? What does that mean in terms of degrees? We might not understand what that means. Okay, so that error function, sometimes people call it a loss, and that's when we do the next project, that's what they call it in Keras, the software we use. So that loss might not be understandable. There might be another measurement that might be more understandable for us. So actually, I talked about this last time, this figure here, okay? This is the mean absolute error, okay? And this, I can't remember. I guess I had this was using the error function, pretty sure. I can't even remember which one I did. It doesn't really matter for this one whether you're doing the error function or whether you're doing the degrees. I'm pretty sure I did the error function, okay? Because you're just interested that it's getting better over time, and you're wanting to wait. If the validation error gets to starts going up, we want to stop. Okay, but for this graph, okay, I think it's better for us to have our errors in degrees, mean absolute error in degrees. Okay, I can't remember. I swear, I think I did this one in degrees too. I think they were all in degrees. I didn't actually write that there, but I'm not sure. But in any case, this one we probably want this one in degrees. That'll help us visualize what's going on better. And definitely want this one in degrees. So this is looking at what is the actual angle and how much is there in error. Okay, so it's this concept of the error function versus some sort of more recognizable thing for us. Because remember, of course, the error function is the sum squared error. Okay, sum squared error. And the mean absolute error in degrees is more understandable for us to know how close we're getting and whether we're doing well. Okay, and so it's going to be a good parallel for when we talk about the next project, where there's one thing talking about the loss. They have another one called an accuracy. Okay, and they're measuring basically the same thing, but the accuracy is in like units that we can understand, and the loss is in some strange thing we just want to make it small, is all we know. Okay, all right. So that's what I got for today. I don't have any more formalized lectures to give, so next time we'll talk maybe a little bit more depth of the things we're expecting here, but I've mostly covered it. Do you guys have any questions so far? Any issues you've run into starting off? Maybe not. Haven't gotten really feet under you yet probably on this one. You did get it rotated? Okay, so that's good. Okay. And I think, did I put in here some string handling with the, I didn't put that in here. So that is one thing, because I did make, I don't have my spider open, but I'm pretty sure I made a little test program to parse out the file names, just to give you a little kickstart on how to get the file names to work out. Where that last little bit is an integer for the number of degrees. I thought I had put that in the description. It looks like I maybe haven't. So that's maybe what I'll go over next time. Or we'll see if we have how much time we have now. Let's see, in the Roomba example, convert names. Is that what I did? Where did I put that? Yeah, that's just converting the names. I swear I made a little thing. That's the wrong place. No, not there. Well, I'll have to look, because I know I made something. I must put it in an odd place. Put it in here, but I'll look. I'll give you a little bit, because you can use, there's like string find commands and stuff, and I'll just show you an example of that to make it easy for you to be able to parse out that. But I'll have a look. I'll make sure we get that for next time. Okay. Question.
Would you recommend any other transforms besides the rotation?
I think for this one, let's just go with the rotation, because in the end, I have another third file. I gave you 2 files, and my test set is another file with those rotations. So it's going to be that same thing. So I'm not coming up with a bunch of new stuff, and there's some errors involved. I mean, because the original image that I got, I asked my students to take pictures of the Roomba, and the original image, it was just, the Roomba was oriented however. And I sort of eyeballed it to get it at the center of the image and at the angle of 0. So it's not even exactly at a 0 angle and not exactly centered.
I was thinking about maybe doing a PCA transform to start off, see if it helps at all.
Yeah. Sure, you're welcome to do that. So the errors that you get. I mean, in the training set, I was getting somewhere. Well, I don't know. I said you had to get within 1.5 degrees on average. I mean, I don't even know how close the original is. I mean, the original is probably within a few fractions of a degree. I don't know. It may be 0.4 away from being at 0.4 degrees away. I don't know. So there's some error involved in that as well. So we just want to get sort of close. All right. So that thing's still blinking down there. So that's a